Okay, this is the video for 8.3. In this video, we're talking about geometric sequences in series. So last time we talked about an arithmetic sequence, and you remember that each time there was a certain amount. So from here to here, we subtracted 7. We subtracted 7 again. From here, we subtracted 7 again, and so on, right? Well, in a geometric sequence, we're not adding or subtracting the same number every time. We're multiplying. So from 1 to 4, we multiply by 4. And from 4 to 16, we multiply by 4. From 16 to 64, we multiply by 4. And 64 times 4 is 256, so we multiply by 4, right? So that makes it a geometric sequence. So in an arithmetic sequence, the common difference we called it D for the common difference. Oh, well, that's weird handwriting. Oh, that looks terrible. Sorry. And in this one, we call it R for the common ratio. So a ratio is a fraction, right? And so every time, if we look at each term and make a fraction of 1 divided by the previous term, that would give us our common ratio. So, for example, if we start with 16 and divide it by 4, the previous term, that would equal 4. And it's also true that if we took 256 and divided it by 64, that's going to equal 4. So any term divided by its previous term will be our common ratio. All right, so I want you to look at these 3 problems. They're on your paper. And determine in each case whether they're arithmetic, geometric, or neither. So pause the video and go do that. Come back and we'll talk about them. Okay, so we look at these. So 21 to 16, we can think about, we've subtracted 5, right? From 16 to 11, we subtracted 5. From 11 to 6, we subtracted 5. So that makes this one arithmetic. So from 3 to 9, we add 6. And from 9 to 15, we add 6. But from 15 to 20, we only add 5. So it's not arithmetic, right? So 3 to 9, we multiply by 3. From 9 to 15, we would have to keep multiplying by 3, but if we multiply 9 by 3, we should get 27. So it's not geometric. So this one is neither. All right, so this last one, if we're adding, we would add 6 to get 12, but then we have to add 12, so it's not arithmetic. If we go from 6 to 12 multiplying, we would times by 2. And from 12 to 24, we would times by 2. And from 24 to 48, we would times by 2. So it is geometric. And R is equal to 2. So a geometric sequence can be thought of as this sequence of terms that are exponential terms, right? So we have a sub 1, there's our first term, and then we multiply a sub 1 by r, whatever that r is, to get our second term. And then we take that second term, so remember we're taking a sub 1 r, and we're multiplying it by r again to get the third term. So that is a sub 1 r squared. And then I take that third term and multiply by r again, and that gives me a sub 1r cubed. And a sub 1r fourth is the next one, and so on. Okay, so a sub 1 is this first term again, just like before, and r is the common ratio in this case, right? So in any time, this is what I was talking about before, that any time you want to find r, so a sub n plus 1 would be the term right after a sub n. You take any term, divide it by the number right before it, and that would be our r. Okay, so let's find the common ratio. So in each case, we would take any term. So say we start with 0.5, we divide by 1. So that answer would be 0.5. Now, what we hope is that we get the same thing again, right? So 0.25 divided by 0.5, that is going to give us 0.5 again. And it's true as well that if we did 0.125 and divide that by 0.25, we also get 0.5. So that ratio, that common ratio, which we call r, is going to be 0.5. Okay, so here's some more. This time we're just gonna deal with geometric or not geometric. Okay, so is it geometric? Then tell me what the common ratio is. If it is not geometric, then you don't have to tell me anything. Except for maybe you could be thinking in your head about why. So pause the video and do these 3 problems and see if you can tell whether it's geometric or not. All right, hopefully you were able to figure it out. So if I take the common ratio, if I take the ratio of 9 divided by 12, so if I put 3 into those, that's going to be 3/4. Okay, and so then I'm going to do 6 divided by 9. Well, I simplify that and I'll get 2/3. So 3/4 is not equal to 2/3. So this is not geometric. All right, let's try the next one. So if I do 3 divided by 9, that's going to simplify to be 1/3. And if I do 1 divided by 3, that's going to simplify to be 1/3. Well, same thing. So it's looking pretty good. Let's try the last one. -3 divided by 1. Oh, yeah, that's not the same at all, right? So this is just -3. They're not the same, so this is not geometric. So just because the first 2 work doesn't mean that the whole thing will work. All right, so this one will be 5 divided by 25. Okay, so that's 1/5. And then we have 1 divided by 5, so that's 1/5. And then we have 1/5 divided by 1, which is 1/5. So every one that's listed here has that same ratio, so we have to assume that it continues. So the ratio is 1/5. Okay, so here are the first 3 terms of a geometric sequence. I'm telling you that it's geometric. I want you to find the next 2 terms. So pause the video for a second and see if you can figure that out. Come back and we'll talk about it. Okay, so first of all, we would want to see what our R value is. So if I take 32 and divide by negative 64, well, the negatives are going to make it a positive, and 32 over 64 is 1/2. So every time I'm multiplying by 1/2. So the next term after negative 16 is going to be negative 8, because that multiply it by 1/2, and the fifth term will be negative 4. You could keep going if you wanted. The next one will be negative 2. Okay, so here's first three terms of a geometric sequence. So find the next two. Pause the video for a second and see if you can do it. All right, so when we're looking to see r here, you notice there's a negative. So negative 10 over 5 is negative 2. So it looks like every time we're multiplying by negative 2, since I've already told you it's geometric, we don't really have to check the other one, but it would turn out, it turns 20 over 10 and 20 over negative 10. It also gives us a negative 2. So our next term will be negative 40. So I'm multiplying by negative 2, and then multiply negative 40 by negative 2 gives me positive 80. Oh, so the 21st term of the geometric sequence. So, well, it's pretty easy to see that my r is equal to 3, but I don't really want to have to do 21 cases. So we need to have an equation that allows us, we need to have the general equation. So let's kind of look at the pattern here. So 3 is our r, so when we have a sub 1, I've got a sub 1 times 3 to the 0, which is 1, right? Here, this would be a sub 2. This would be a sub 3. Here's a sub 4. In case the very next one would be negative 162. And you notice that every time I'm just including an additional r, right? So if we look at that in general terms, a sub 1, let me just get rid of my writing here. A sub 1 is a sub 1 times r to the 0. A sub 2 is a sub 1 times r to the 1. A sub 3 is a sub 1 times r to the 2nd. You see the pattern? You see how every time it is? So what would it be if it were n? A sub n is a sub 1 times r to the, what comes right before n? So it would be n minus 1. Okay, so always you notice that whatever this a sub n was, this was 1 less. And so that's what how we write it is an n minus 1. That would be the number right before n. All right, so this is a important equation. You should probably have this on your note card. Okay, so now we're back to our problem. So we want the 21st term. So we want a sub 21. Okay, so I know that a sub 1 is negative 2, right? And then I'm going to have r, which is, remember, 3, to the 1 less than whatever one we're doing, to the 20th. So that is a pretty big number. For a lot of calculators probably won't do it. We'll see. I think mine will do it. All right, so it's going to be negative 6. What are we up to? figure out. 6, 9, 7, 3. That's a 3. Sorry. 5, 6, 8, 8, 0, 2. There's the million. So 6,973,568,802. That's the thing about geometric sequences, is they get big in the same way that like exponentials would get really big, right? Okay, I want you to find the 11th term. So pause the video and use that formula and see if you can find a sub 11. All right, hopefully you found it. A sub 11. So that means n is 11, right? So we're going to do a sub 1. That would be my 7. Now, what is my r? So I'm looking at 35 divided by 7. Should be 5. And if you want to double check, you could plug in 175 divided by 35, and that should be 5 as well. Right? So r is 5. Raised to the power of 10. So it is 1 less than our 11, right? So 5 to the 10th times 7. So not nearly so big since it's only to the 10th. 5, 9, 3, 7, 5. 359,375. There we go. Okay, so here's one more. Pause the video and see if you can try it. This time it didn't give us the actual sequence, but it gave us all the important information that we needed. So pause the video and see if you can find that. Okay, we're looking for a sub 10. So that's going to be the first term. They said that was 5. Times r, so that's our 2/3. To the 9th power. All right, so see if we do 2 to the 9th. That is 512. Oops. And 3 to the 9th. That is 19,683. And I would just need to multiply those top numbers together. So 512 times 5 is 2560. Is that really true? Yep. Huh. Okay. Okay, so here's one more. Finding a specific. So we know that a sub 1 is 17/9, and the fourth term is equal to 51. Find the value of the seventh term. Okay, so we want to keep our answers as fractions we want to use fractions, not decimals, because, you know, if you plug in 17/9 to start off, then we would have repeating decimals and never ending. We'd have to round off, and then we would have an error. Okay. All right. So So let's look at our equation. Remember our equation. So here's what I know. What I don't know is I don't know r, right? So I'm going to have to try to find r. But I do know the fourth term, and I know the first term. So if I just use that, a sub 4 is 51. That's a sub 4. That should be equal to a sub 1, right, which is 17/9 times r to the 4 minus 1. So that's going to be to the third power. All right, so let's multiply both sides by 9 over 17. That'll get rid of that. And we have 9 times 51 is 459 over 17. And that's equal to r cubed. So let's just see if 17 will reduce in there, and it does. So that means 27 is equal to r cubed. And 27 is a perfect cube, so r is equal to 3. Now you probably could have gone through and done some guessing, but with that fraction there, that's not so easy. Some of them might be easy enough, but this was a direct way that we could solve for r, because we had all that information, right? So now that we have that information, I can just write the seventh term, right? So a sub 7 is equal to a sub 1, which is 17 over 9, times r, which is 3, raised to the 7 minus 1, or 6th power. Okay, so we will take 3 to the 6th. That's going to be 729. And that's got a lot of 3's in it, so I know it will reduce with that 9. So I'll divide by 9. That's going to be 81. So 81 times 17 is 1377. And that is the 7th term. So we sometimes don't know the first term. And so just like we did with the arithmetic sequence, we can write this equation for a sub n using some other term, right? So we can pick whatever term we want. Whichever term it is, that's our k, and we can put that into this equation, just like we did before with the arithmetic, right? So this is a helpful equation that you might want to have written down. Okay, so here's a problem there where we might use that. Okay, so in this one, we know the common ratio, and we know the 7th term, but we don't know the first term. Okay, so we're trying to find the 11th term. So we'll take a sub 11, and this time we want a sub k. So remember, we're using this equation. It's on your paper, but it's not on mine. Okay, so we take a sub 11 equals a sub k, so that's the 7th term, negative 37, times r, which is negative 3, to the n, which is 11, minus 7, which is our k. All right, so we've got negative 37 times negative 3 to the 4th power. So it's an even power, so that's going to turn out to be a positive number. 3 to the 4th is 81, so we're going to do negative 37 times 81. And that will give us negative 2997. Sorry, that is, sometimes these are so messy. Okay, all right, so that's how we can do it if we don't have the first term. All right, so let's talk about series, right, or that sum. So just like with the arithmetic, we do have a formula. It's not quite so easy to derive, so I'm not going to derive it for you. It will make this video way too long. So, but here's how it looks. We have our first term. There's our first term, right? Or you can put it on the top if you want. Sometimes you see this formula with it written on the top. And then you have 1 minus r to the nth. And as it mentions down here in words, if we bring that a sub 1 on top, we have a sub 1 times 1, that's the first term. And a sub 1 times r to the n, that's the n plus 1th term. That's kind of what we're looking at when we we're kind of saying it in words. And then on the bottom, we have 1 minus the common ratio. So let's see how that works out. This is another one of those those equations you might have to use. Okay, so these are written for you in the form where everything is clear, right? So the fact that this exponent is a 5 means that this is the 6th term, right? So this is the 6th term. So n is equal to 6. I'm looking for s sub 6. Okay, so I also know the first term, a sub 1, is 3. And r is negative 3. So a sub 1 is 3, and r is negative 3. So we keep track of that. And let's see, I don't know that I better write down my equation because I don't have it sitting in front of me like you probably do. And then I have 1 minus r to the nth over 1 minus r. Okay, so I have a sub 1, which is 3, and then I'll have 1 minus r to the n, so negative 3 to the 6th over 1 minus negative 3. Okay, so I have 3, and so 3 to the 6th, I think it's going to be a positive because it's an even exponent. I think we already did this, and it's 81. No, it's 729, sorry. 3 to the 4th would be. All right, so that's going to be 1 minus 729 over 4. So that will be 3 times negative 728 over 4. And when we plug that in, we've got negative 728 times 3. The top is negative 2184. And we divide that by 4. and that will be negative 546. So is that okay to have a negative? Well, yes, it is, because you notice that every other term up here is going to be negative. And so this last term is also negative, so that's the biggest one yet. So it's going to have made it pretty negative, right? So negatives are fine if there are negatives in our answers, in our series, right? Okay, so here's one for you to try. Make sure you leave your answer as a fraction. Try it and come back. All right, so this 7 here means that our n is equal to 8. That's the term we're looking for. A sub 1 is equal to 4, and r is equal to negative 1/3. All right, so we're looking for the sum of the first 8 terms. So I'm going to have a sub 1, which is 4. That'll be 1 minus r to the n, which is 8, over 1 minus negative 1/3. So here's where you probably ran into problems with the fractions. But so 1/3, I would take 1 to the 8th and 3 to the 8th. So this is going to be 4 times 1. This is going to be a positive, so we'll still have our negative there. And it's going to be 1 over 65, 61 over, I'm going to combine these and get 4/3. All right, so think about this. So 1 is 65, 61 over 65, 61. And I'm subtracting that number. I better write it up here. I have one more room. So this is going to be 65, 60 over 65, 61 over 4/3. So when we divide by a fraction, we're going to invert and multiply, right? So this is the same as we're going to multiply by 3 over 4. So these 4's will cancel. So now I've got 3 times 65, 60 over 65, 61. And we could multiply this. Let's just double check and see whether or not 65, 61 is divisible by 3, so we can reduce. Yes, it is. So this will now be 2187. So this answer will be 6560 over 2187. Okay, so sometimes we get them in a little bit different form. So here is our sum, our summation notation, right? So again, we're looking for, we need to know n, and we're going to have 12 terms. So we're looking for s sub 12, and n is 12. And r, what do you think r is going to be? Well, this is just a little bit off, right? Things are just not exactly on. So basically, let's find r by plugging in the first 2 terms, right? So a sub 1, I'll plug in 1 for j, that's going to be a 2. And then when I plug in 2, I get 2 squared, and that's going to be 4. And if I just want to do one more, 3, that's going to be 8. So my terms are going to be, so 2, 4, 8. You see that every time I'm multiplying by 2. So this number here that was raised to the power, that was still our r. It was just that, think about in our normal equation, we have our a sub 1 times r to the n minus 1. And if I multiply these together, I get 2 to the 1 times 2 to the n minus 1. They have the same base, so now it's going to be 2 to the n. And that's what happened. That's what happened here. Okay, so my a sub 1 is 2, and my r is 2. Okay, so a sub 1 is 2, and that's going to be 1 minus r, which is 2, to the nth, which is 12, over 1 minus 2. All right, so I've got 2 times, so let's see, 2 to the 12. I'm pretty sure I can fit this in here. That's going to be, oh, that's not that big, 4,096. So it's going to be 1 minus 4,090, oops, 4, forgot the 0. 4,096, and that's going to be over negative 1. Okay, so that's going to be 2 times negative 4,095 over negative 1. So that negative 1 on the bottom, that's just going to take care of the negative on the top, right? So I got 4,095 times 2. It's going to be 8,190. Okay, and it's positive because I had that negative on top and the negative on the bottom. So that would be the sum. One more. So pause the video and see if you can figure out all the information that we need to have for this and find that sum. All right, so n is going to be 8, a sub 1, and r. All right, so r is going to be that 1/4. And if you plug the 1 in there, you see that a sub 1 is 1/4. All right, so the sum of the first 8 terms is going to be a sub 1, which is 1/4, 1 minus r, which is 1/4, to the n, which is 8, over 1 minus 1/4. So this is going to be 1 over, so I got 4 to the 8th is 65, 536 over 3/4. So while I'm at it, we might just as well invert this and multiply it by, dividing by 3/4 is the same as multiplying by 4/3. And these 4's will cancel, and now I just have a 1/3. And then 1 is going to be 65,536 over 65,536. And so when I subtract that, it will be 65,535 over 65, 536. Let's just see if we can't take a 3 out of there. So when I divide the 3 out, I get 21,845. So that will be our numerator, 21,845 over 65, 536. Okay, so far all we've done are these finite sums, but with geometric sequences, there are some times when it makes sense to have an infinite sum. Right, so in this case, let's think about this one. Okay, so this is a geometric series we're adding together, and and here's another geometric series, right? But there's something very different about these. So I'm going to draw pictures here as we do. That is our 1. There's one whole, right? And in the next one, I have a 1/2. That would be the blue one, right? A 1/4. That would be the orange one. A 1/8, which would be half of what's left. That would be the green one. A 1/16 would be half of what's left of that. That would be the yellow one. And so on. Every time I would be taking up half of what's left, and I would never actually get there except that I'm going infinitely. And you see how the further along I go, the closer and closer I get to having an equal 2 whole units here. But I'll never go more, because every time the next term is going to equal half of whatever is left. So this really does equal 2. Now, let's look at the other one. Well, the first one is 1. The second one has 2. The next one is going to have 4 more and 6 and 8 more and then 16 more. And it doesn't approach anything, right? It just keeps getting bigger and bigger and bigger. So this one is infinite. It doesn't have a sum. Okay, we actually call we call the one like this one, we call the first one convergent. Okay, so if we look at what happens as we keep adding on the next term and the next term, it converges on a certain number. And because we're doing it infinitely, we can say it's that, right? In this other one, in the second one, we call it divergent because it just keeps on growing. It just grows and grows and grows. It doesn't approach anything. It just keeps getting bigger and bigger and bigger. So the thing that you may have noticed about these is what R is. So let's just take a look at what R is in this first one. So you go from 1 to 1/2 is multiplying by 1/2. From 1/2 to 1/4 is multiplying by 1/2, right? So R is equal to 1/2 here, right? But whereas in this other one, R is equal to 2. And that's the key. We only have a convergent series if R is less than 1. Well, it could be negative, but it would have to be in between -1 and 1. So R has to be greater than -1 and less than 1 in order for us to have it having a sum. Okay? Now, when we look at it, remember, so here's how we often say it is the absolute value of R is less than 1. Okay, if R is equal to 1, then it doesn't converge because it would always be the same number, right? Here's what it looks like. Now let's think about what happened in our previous one. So when we had the finite one, the only difference is on the top we had 1 minus r to the nth, right? So think about what happens as n gets really big and r is a fraction. Well, if r is a fraction and we take it to a really big power, it gets really, really small. It gets really close to 0. So this whole thing approaches 0. And so all we're left with is just the 1 on top, right? So that's why when we talk about it going to infinity, and it only happens if r is a fraction less than 1 or greater than -1, then this is what it comes down to. So this is definitely one of the formulas that you'll want to have. And we actually find a lot of places where we can use this. So first of all, let's just see how it works here. All we need to know is r and the first term, right? And then we can find it. And so, but r has to be between -1 and 1 in order for it to work, right? So in this case, let's see first of all what r is. So to go to 10 to 2, I'm dividing by 5, right? So 1/5. And sure enough, from 2 to 2/5, that's multiplying by 1/5. So r is 1/5. So does that meet our requirements? Yes, it is less than 1, right? So then the first term is 10. So the infinite sum is going to be the first term over 1 minus r. So whenever we have this 1 minus r, you can think about the 1 being 5 over 5 minus 1 over 5. So I've got 10 over 4 over 5. And dividing by 4/5 is the same thing as multiplying by 5/4. So I will have 50/4. Or divide by 2, 25/2. Okay? So this is the infinite sum. So this will keep going forever, but it's going to get closer and closer to this number. It's never going to go past it. It's just going to get closer and closer to that number. Now what about this one? What's r? First of all, we find r. And r is, we're looking at 8 over 4, right? 16 over 8, so r is 2. Does it meet our requirements? No. The absolute value of 2 is not less than 1, right? So this one, there is no sum. Okay, now this is an interesting one. So let's figure out what our r is first and see whether it meets our qualifications. So r is going to be 0.09 divided by 0.9. So you can think of this however you want. I'd like to multiply by 10. You might multiply by 10, and then you'll know you have 0.9 over 9. Or you could multiply by 100, and I would have 9 over 90, which reduces to 1/10. Or you can think of it as 0.1. So perfectly fine to do the decimal in this case because it's not repeating. Okay, so our r is 0.1. So does that meet our criteria? Yes, that is less than 1. So our infinite sum is a sub 1, which is 0.9 over 1 minus 0.1. So 1 minus 0.1 is 0.9. So that's going to equal 1. So I don't know if you noticed, but this is the same as, look, if we actually added these together, I would have 0.999. Since all these are in a different decimal place, we'll just have the 999s. It goes forever. And did you know that? 0.999999 is equal to 1. If it keeps going forever, it's equal to 1. If we stop it at any point, then it's not quite equal to 1. But if we let it go forever, it's equal to 1. And we can discuss that more when we get together if you have a problem with that. It's kind of a mind-blowing concept. This is our very last one. We're going to compute this last sum. Oh, where is it? Okay, there it is. All right, so what do we know? We need to know a sub 1. Well, first of all, what's r? We better figure out r first. Okay, so r, remember, is the one that goes in here. That's our r. And a sub 1 is going to be whatever we get when we plug in 1. So that's going to be 3/8 times 2/3, because this is not a k minus 1. This is just a k. All right, so the 3's will cancel, and the 2 will cancel with the 4, and we're left with 1/4. So does that meet our criteria? Yes. Yes, it does. And so our infinite sum is going to be a sub 1, which is 1/4, divided by 1 minus 2/3. Okay, so 1 minus 2/3, so 1 is 3/3 minus 2/3, so that's going to be 1/4 over 1/3. I will invert. Dividing by 1/3 is the same thing as multiplying by 3 over 1, so I have 3 over 4. And that is our sum. So try some of these out. I would love to talk about this a little bit more, especially about the 0.999 repeating being equal to 1. And we can try some other ones like that. And that is also a way that we can take a repeating decimal and change it into a fraction. So I will see you in class. Bye.